And our first talk is from James Rogers from Cambridge, and he will be talking about the impact of stellar evolution on the Radius Valley.
Okay, great. Thank you very much, everyone. Yeah, it's a real privilege to talk to you today about the Radius Valley and the physical impacts of stellar evolution and how we get to the Radius Valley. So we've seen the Radius Valley come up so many times in this conference, and we're going to see it even more, I imagine. Allow me to show it to you one more time. I think this is probably one of the greatest legacies of the Kepler Space Observatory. We see the radial distribution in the small close-in exoplanets. And we see this population here that we call the super-Earths at about 1.3 times the size of Earth. And we see another population at about 2.4 times the size of Earth. And in between, we see the Radius Valley. There's this lack of planets. And it's a really interesting feature to try and understand its origins and why it formed. It's always instructive to look at the Radius Valley also as a function of orbital period. So we see, again, the population of super-Earths here below the Radius Valley, and then we see the population of sub-Neptunes above the valley. And notice that there's a slope to the valley, which indicates that there's probably something to do with installation that these planets are receiving that is something to do with forming this distribution. So to really put in perspective how irradiated these planets are, something I like to show, and I'm certainly not the first person to make a slide like this, I like to show things to scale. Right? So here I'm going to draw a little solar system. So this is a solar mass star, for example. NASA's Parker probe made its closest approach to our sun in December of last year. It was a distance of about 4 million miles. It's about 10 to 11 solar radii away from the surface of our own sun. And the irradiation environment that it received was absolutely incredible. You may have seen how this mission was advertised. It was a mission to touch the sun. And you can see, right, this is an onboard video of what it's seeing. You can see the corpuscular action that's happening there. So let's make Parker probe to scale. We can't see it, right? A pretty typical hot super-Earth is going to sit about here relative to Parker probe. So Currit 7b is not an outlier. It's a hot super-Earth, but it sits at about 2 to 3 solar radii away from the surface of our own sun. So the irradiation environment that these planets are sitting in is really, really extreme, unlike anything really in our own solar system. And it leads to processes like photoevaporation. We've heard about photoevaporation this morning, so I'll quickly just go through this mechanism. So I'm going to assume for the first part of this talk that these sub-Neptunes are Earth-like interiors with hydrogen-dominated envelopes on top. I'm going to come back to reassess this assumption towards the second half of this talk, but for now, let's assume sub-Neptunes are Earth-like interiors with hydrogen-dominated envelopes. Remember that these planets are super close into their host stars, and particularly during the early evolution of these stars, the irradiation in the EV and X-ray flux is very, very extreme. We saw earlier in the week that we think stars begin in a saturated regime where the output of X-ray luminosity is very high when the magnetic activity is high. And so these photons heat and ionize the hydrogen atoms and molecules in the envelope, and you can drive a very, very powerful hydrodynamic outflow. Now, a hydrodynamic outflow is very different to what Earth is experiencing right now. Earth loses about 100 tons of material every day to something called Jeans escape, or something sometimes called ballistic escape. And this is where the particles at the very rarefied top of the atmosphere have enough kinetic energy just to escape on their own, unhindered. We sometimes say their collisional mean-free path is way shorter than a scale height, so they can just escape on their own. This is different. What we're looking at here is the envelope leaving as a fluid. We can say that the gas is still collisional and is leaving en masse. And as a result, the mass loss rates are way, way higher than what we experience on Earth. And many studies have shown that you can completely strip this hydrogen-dominated envelope to produce a super-Earth. And so the idea of these mass loss processes is that we form the Radius Valley by starting with a progenitor population of sub-Neptunes, and then some of the planets, particularly the ones with a smaller mass or more irradiated planets, form the super-Earths. So population models do a really good job of reproducing the data. On the left is the data from the California Kepler survey, and on the right is a population model. You see we reproduce this slope as a function of orbital period, and we get the two populations of super-Earths and sub-Neptunes. So photoapparition does a great job in reproducing the data, but you may have seen in the literature there's this other mechanism which also does a good job, called core-powered mass loss. Now, I'm of the opinion that core-powered mass loss is actually quite a misleading name for the process, because it suggests that the core powers the mass loss, which is actually not true. Core-powered mass loss does not work without the star. The difference that, unlike photoapparition works through EV and X-ray flux, core-powered mass loss works through bolometric heating from the host star. Again, if you just had a planet in isolation and you had a hot core, you would not form the radius valley. Core-powered mass loss does not work without the host star. The insight from core-powered mass loss, however, is that when these cores formed in a protoplanetary disk, they store a lot of energy, a lot of thermal energy inside. We formed the solid core, material accreted on, transitioning binding energy into thermal energy, and then you put a hydrogen envelope on top, which is very optically thick, which stores all this energy inside. And what that thermal energy does is it puffs up the planet. It increases the size or resists contraction. And as we know from mass loss models, the mass loss rate of a planet is exponentially sensitive to the size of the planet. So if you can maintain the puffiness of your planet just a little bit, you increase the mass loss rates sufficiently. And again, we can drive very similar hydrodynamic outflows through core-powered mass loss. If I could go back to 2018 and maybe rename the name, I would call it core-assisted bolometric mass loss, which is just not as catchy, but you get the idea. So because both of these models are based on hydrodynamic outflow, they both reproduce the radius valley in very similar ways. Again, both models reproduce this slope as a function of orbital period. One of the ways that was suggested we can try and distinguish between these two models is on the timescale that these envelopes are lost. So photoapparition, usually we think acts mostly on 100 million year timescales, and core-powered mass loss was predicted to work on gigayear timescales. And whilst this is true if you think about the two models in isolation, it's actually not true when you think about the two self-consistently. So I'm going to come back to this prediction in a few slides. For now, what I want to do is think about an evolutionary process or an evolutionary timeline for these sub-Neptunes. And this joke was actually scooped from me yesterday by Vincent. To understand the evolution of these planets, we need to know thy star, know thy protoplanetary disk, and also the planet, all right? But I'm glad it was said, because I agree. So we think these planets formed in protoplanetary disks. They began by forming a solid core. When that core was massive enough, typically something like the mass of Mars, it has a deep enough gravitational well to hold on to a hydrogen-dominated envelope. So we go through gas accretion. These protoplanetary disks don't survive forever. They have lifetimes somewhere between 3 and 10 million years. But when they disperse very, very quickly on a timescale of maybe 10 to the 5 years or 100,000 years. So this is a very quick astrophysical process, and it induces this mass loss event that we call boil-off. And I want to spend a bit of time talking about boil-off in a second. But we think this is probably the most dominant phase of mass loss that these planets go through, and it's after boil-off that we go through events like photoapparition and core-powered mass loss. So let's have a think about boil-off. So as I said, these planets are in the protoplanetary disk. They're cooling and accreting material. This idea of a Bondi radius is going to be important, not just for this, but later down the line in the talk. The Bondi radius is roughly the delineation where material has enough thermal energy to escape on its own. It's no longer thermally bound to the planet. So the way that accretion works is that the planet cools, contracts, and you can then squeeze a little bit more material within your Bondi radius. As I said, the disk disperses very, very quickly on a timescale of about 10 to the 5 years. And that means that the confining pressure that these planets have been happily sitting in from the gas disk suddenly disappears. And what happens is that the planet, the only option it has is to adiabatically expand its envelope and push a lot of material above the Bondi radius. As I've just said, that material is no longer thermally bound, so we lose that atmosphere. And initial models showed that you can lose nearly 90% of your envelope mass through disk dispersal. So we put out some self-consistent models last year where we not only modeled boil-off, but also the accretion phase. So as a function of time, I'm showing the envelope mass fraction. So this is the mass of the envelope divided by the mass of the core. And you see the planet initially accretes maybe tens of percent of envelope mass, and then the disk disperses, and we very rapidly lose the vast majority of our envelope mass. So we think boil-off is very important. And this puts us now in a position to try and understand the transition between these three mass loss mechanisms that I've been talking about. To understand the transition, we need to think about two energy sources in the planet. The first is the internal luminosity that's driving the thermal evolution of the planet, so the interior luminosity of the planet, and then what's heating the upper atmosphere of the planet. During boil-off, the interior luminosity is driven by thermal contraction of the envelope. Again, the envelope is very massive at this point. As the disk starts to disperse, it contracts, and that changes binding energy into thermal energy, which resists against contraction. This is sometimes called Kelvin-Helmholtz contraction in stellar physics, right? And at the top of the atmosphere during boil-off, we're heated by the bolometric heating from the local disk, which is also being heated by the star. So this is a nice definition of boil-off here. The transition to core-powered mass loss comes when the dominant luminosity source inside the planet is now driven by the core cooling. So instead of the thermal contraction of the envelope, it's now driven by the luminosity of this hot core that is, again, resisting contraction of the envelope. But again, as I said, core-powered mass loss doesn't work without the bolometric heating. And at this point, the disk is probably still has a little bit more dispersal to go. So we're still in this bolometric-driven outflow. The transition to photoevaporation, we can understand as where the X-rays are coming from. So if you imagine the line of sight between your sub-Neptune in a dispersing disk to the star is currently optically thick to X-rays. There's too much disk in the way to actually drive a photoevaporative XUV outflow. And another reason I introduced the Bondi radius earlier is because for a bolometrically heated outflow, the Bondi radius also delineates the transition where the outflow goes from subsonic to supersonic. So this is the point at which the outflow material becomes supersonic. If the X-rays are heating a supersonic regime of outflow, that information about X-ray heating can't be moved interior to the planet because they're causally disconnected. But once the disk is fully dispersed and the planet has contracted sufficiently, these X-rays are going to start to penetrate into a subsonic region of the outflow. And suddenly now, the heating is driven by XUV heating and can actually tell the planet, they're causally connected. It can tell the planet, you are being XUV heated, you're going to be driven by photoevaporation. So this is what I want one of the main takeaways from this talk to be, is that we think that for most sub-Neptunes, this is probably the evolutionary timeline that we're expecting, given a self-consistent thinking of these mass loss processes. So we're going from boil-off and core-powered mass loss, which are bolometrically driven, to photoevaporation once the disk is dispersed, and this is XUV mass loss. So it's actually the other way around than when you think about these processes individually. There are ways of changing this order subtly, so that's why I put this little bit of small print down here, that there are ways of changing this order for some planets, and so if you're interested, I'm going to point you to these papers over here, which go into that in a lot more detail. For the second part of the talk, I want to come back to an assumption that I made at the very start and reassess it, and that is, what are these sub-Neptunes actually made of? So far, what I've spoken about is that these sub-Neptunes are Earth-like interiors with hydrogen, helium-dominated envelopes. And this might not actually be the correct assumption. So something we did in 2023 was you looked at the mass radius diagram, and we highlighted the sub-Neptunes, and we said, if they are in this scenario of Earth-like interiors with hydrogen-dominated envelopes, I'm going to call this the gas dwarf scenario, then these planets should sit between the dotted lines and should mostly cluster very roughly along with this dashed line. And broadly speaking, this is what we see. So that in the mass radius diagram, we're consistent with this gas dwarf scenario. The issue is, it's completely degenerate, and we've seen this a couple of times this week, with another scenario, which I'm going to call the water world scenario. And this is where these sub-Neptunes are actually made of a rocky interior with a very large water mass fraction, something like 50%. And again, this is all because of this degeneracy where you can explain the mass and radius of a given planet using very different interior compositions. And so it seems like the field is being asked this million-dollar question right now. Are sub-Neptunes gas dwarfs, Earth-like interiors with hydrogen, helium-rich envelopes, or are they water worlds, 50% rock, 50% water? And we really want to answer this question because the implications are quite profound, I think. In that, if it's the gas dwarf scenario, we're saying the radius valley emerged as a product of evolution, in that things started as a progenitor sub-Neptune population, and then some of them transitioned to super-Earths. I should mention the talks we heard from Eve Lee and Vincent earlier in the week about the primordial radius gap are still within this framework of gas dwarfs. Really, the gas dwarf scenario is saying that the radius valley exists either because of a presence or a lack of a hydrogen envelope around these rocky interiors. The water world scenario is different. It's saying that there are two very distinct formation pathways and that the radius valley is a delineation between how these planets form. They have very fundamentally different interior compositions. So we want to know the answer. We can't phone a friend. So we are going to phone a friend. We're going to ask transit spectroscopy, can it help us? So what is transit spectroscopy actually probing? We're probing the mean molecular weight of the envelope of the upper atmosphere. And the predictions of these two models, from a theory point of view, is that the gas dwarf model would predict a mean molecular weight of something between solar metallicity gas and slightly elevated, something like a mean molecular weight of 5 atomic mass units. The reason it can increase is because you can have magma-ocean interactions between this silicate-rich magma ocean and a hydrogen-helium-dominated envelope. This can push a lot of oxygen-rich material, metal oxides and water into the envelope and increase the mean molecular weight. And water worlds, which would have a much higher mean molecular weight, something consistent with pure steam, maybe a little bit lower if it's also accreted some hydrogen. I'm running a little bit low on time, so I'm just going to flash these up. Here are just a few examples of estimates of mean molecular weight from current observations. Apologies if I haven't shown your favorite inference of your favorite planet. But you see that the picture is not clear, right? We see a couple of points maybe in the gas dwarf scenario, but we also see planets like GJ 9827d, which seems to be consistent with the water world. So the question of can transit spectroscopy help us answer this question, I think the answer is currently not yet. We're dealing with small number statistics. I still think we're in our infancy of understanding James Webb data, as we've heard earlier this week. So this will certainly play a really important role in answering this question, but I don't think we're there just yet. What I'm going to try and argue in the last part of my talk is that actually young planets can help us answer this question. If we rewind the clock of a sub-Neptune evolution, right, from where we observe them today, maybe around around gigayear timescales, and we rewind the clock, the initial sizes of these planets are going to be very dependent on the mean molecular weight of their envelopes. So if I start with a very low mean molecular weight, something like solar, the initial sizes of the planets can be nearly 10 Earth radii. They're very puffy. Whereas if I start with a high mean molecular weight, they're going to be small. We can understand that just through the scale height. Scale height is the ratio of the sound speed squared to the gravitational acceleration, and it's inversely proportional to the mean molecular weight. So if I increase the mean molecular weight, I decrease the scale height, and my planet barely contracts, and I'm keeping everything else constant in this sub-Neptune. If I model actual gas dwarfs and actual water worlds using this framework, you can see that the gas dwarfs have very low mean molecular weights, and so they should start very, very inflated when they're young. However, they converge after gigayears, and this really highlights that degeneracy that I was talking about in the mass radius diagram. So what I've done here is I've built some population models under both frameworks, the gas dwarf scenario and the water world scenario, remembering that if this is true, we're saying that the radius valley exists because of evolution, and if this is true, the radius valley exists because of formation. And what I'm showing here in the contours, in the colored contours, are survey predictions from the models. And in the gray points, I'm showing actual data from the California Kepler survey. Most Kepler stars we're seeing are somewhere between 1 and 10 gigayears. And I've also applied all the biases and the measurement uncertainty of the California Kepler survey to reproduce all these biases. And you can see that for Kepler, both models reproduce the data really nicely. The other thing to notice is that the color bar here represents the expected yield of the survey. So both models are currently predicting something like 1,000 planets using a Kepler-like survey, and that's exactly what we saw with the California Kepler survey, about 1,000 planets. So given old, evolved stars, this is what we're seeing, and we cannot distinguish between the two models. Now what I'm showing here is a very young subset of planets, and I'm applying a test-like observational bias. And so this comes from a small survey of test planets from Sidney Vac et al. In 2024. And you can see that the sizes that we're predicting to observe gas dwarfs are much, much larger. This is because they have lower mean molecular weights, they're more inflated, and so you see them at these inflated sizes. And the prediction in terms of yield of the gas dwarf scenario given a test-like survey is something between 14 and 18 planets, and TESS has actually observed 14 planets. The water world model, on the other hand, predicts only a very, very small number of detections, between 0 and 2, at something like 2 to 3 Earth radii, and this is because they have high mean molecular weights, which means they never really contract, they don't start puffy. And so the fact that we've observed 14 planets, 14 young planets with TESS, suggests that we're potentially inconsistent with this water world model. So this is tentative evidence that we're probably more on the gas dwarf scenario, but the issue here is that we're dealing with small number statistics, we're still trying to understand TESS as a demographic survey. We're not quite there yet. So wouldn't it be amazing if there was a dedicated transit survey, perhaps from a small Explorer mission concept, to go and actually find these young sub-Neptunes? So we heard from Ward earlier yesterday, actually, about the Early Evolution Explorer, or EVE. One of the science cases for this mission is a dedicated transit survey of very young exoplanet host stars. And we're really trying to actually probe this age range here, less than maybe 100 million years, where exactly these models are not degenerate, where they completely diverge. And so I'm going to argue that young planets really are the way that we can answer this question. I've gone really, really quick through that talk. So my main takeaways, firstly, are that core power mass loss is not core-powered, it's bolometrically powered. The second is that we think that for most sub-Neptunes, this is the evolutionary timeline that one would expect for a gas dwarf model of a sub-Neptune. So boil-off during disdispersal, core power mass loss continues that, and then after that we expect XUV mass loss. And to answer this question of what are sub-Neptunes, are they these water worlds or are they these gas dwarfs? I think young planets, around young stars, and we've heard a lot this week about the difficulties of trying to observe planets around young stars. But I think that is potentially our best way of answering this question. So I will finish there and happily take any questions. Thank you.
Wonderful. Thank you. Oh my gosh, this is actually kind of hard. Do we have a mic? Let's start over there. The mic's over there.
Hi, great talk. Something that's been bugging me for a while, and maybe you have an answer for it, is I think we're learning most sub-Neptunes aren't solar metallicity atmospheres, that they're maybe 100 times solar, and the outflow rate looks very different for 100 times solar metallicity envelope. How do your models of the radius valley and its evolution over time change if you switch everything to 100 times solar?
Yeah, it's going to change a lot. And so that another way to think about metallicity is the mean molecular weight. And so as I was showing, the sizes of these planets are going to be different as a function of time if you change the metallicity of the envelope. You can then, if you increase the metallicity, you can then, if you want to reproduce the radius valley, you can just put more envelope. You can just increase the envelope mass fraction to increase the size. So this is always this double-edged sword thing about these evolution models, is that we can always fit the data with the models by just tuning separate things. But in terms of atmospheric escape, I think understanding atmospheric escape with high mean molecular weight envelopes is still very much in its infancy. Understanding how hydrogen is going to drag other heavier species with it, I think we're still trying to understand. But yeah, I think I agree. We're seeing high metallicity envelopes or atmospheres with James Webb. There's still this degeneracy with cloud top, and if we're probing, and also how the upper atmosphere relates to the lower envelope as well, and in terms of mixing and things like that. So we're still, I think, in our infancy of understanding where this high metallicity picture comes in understanding the interior structure of these planets, and whether you can still form a radius valley through purely atmospheric escape. I think you still can, though. Yeah.
Ray Holcomb, UC Irvine, fantastic talk. I'm wondering if there's been much thinking done about whether this is a process that might be affected by galactic environment, thinking ahead to something like Roman, where we're going to get a bunch of planets in the galactic bulge. If differences in demographics around the radius valley might tell us something about how that all ties together.
Right, yeah. So, so Jesse gave a nice talk earlier this week about thinking about metallicity and galactic position, zip code, right, of where these planets are. Kepler probed a fairly narrow range of metallicity, and we didn't see too much variation in the radius valley as a function of metallicity. But it's going to be really interesting to start probing different areas of the galaxy in terms of how the radius valley behaves. And then this other question of, right, the clusters, and thinking about these young planets, when we're looking at these very young clusters, they formed in a very different environment to the clusters that eventually formed the Kepler population in terms of the age of the galaxy. So I think it's hard to make predictions right now, but bring on Roman and let's let's find out.
Just right behind there.
Thank you for the great talk, James. I was wondering if you look in what is the time scale for the transition between the process of copper mass loss and photoevaporation, and how that would change according to the stellar spectral type.
Yeah, that's a good question. So I should also say that thinking about these mass loss processes self-consistently, we're still very early on in trying to understand them. There's still a lot of work that needs to be done, especially thinking about as we go to different stellar spectra and things like that. From what we were seeing from those initial studies is that it really is dependent on when the thing that transitions you from bolometric-driven mass loss to XUV-driven mass loss is about how much you've contracted as a planet and how optically thin the disk is. So you also have to think about how disks behave around different stars as well, because that will change the output, the outcome. And so again, it's not a great answer, but we don't know yet. I think it's probably fair to say.
Hi, James. Great talk. So you mentioned that this sub-Neptune's population can be explained by the evolution or the formation. So, and it depends on the composition of those planets. I'm curious if there's been any theoretical work done on kind of trying to explain both, and maybe there's some difference that could be made in fundamental understanding of protoplanetary disks. So, for example, the location where those planets get formed, and that could like also give us an answer in this degeneracy. Yeah.
Right. Yeah. No, I completely agree. Right, we're dealing with small number statistics right now with tests. If we can go and get of order 100 planets with something like Eve, we can start probing. Right. I gave those two options in the $1 million question. The answer is a secret C. It could be both. And so if we have a large population, we can start to do mixture models at understanding which is the dominant driver, right? Do you need mostly from one option and then the other? The other thing I think about probing the location in the disk about where things were accreted, I worry about that with small mass planets like sub-Neptunes because the mass reservoir is in the interior, it's the rock. So depending on the metallicity of the gas you accrete may depend on location of the disk, but the chemistry of the interior is going to then dictate the future appearance of the chemistry of the envelope, if that makes sense. So saying that this small planet formed in this part of the disk and it has this C/O ratio may not be true because the interior is just going to change that chemistry instantly. So there's some, but I agree, we can start to probe things about planet formation and maybe the type of disk it formed in. Yeah.
Thank you.